In this video we're going to look at how to solve problems in rotational motion using the 5 equations of rotational kinematics. So you need to get used to these 5 symbols below. This first one here is the theta symbol. It stands for angular displacement. And this one is time, T for time. This one, alpha, stands for angular acceleration. This one is omega F for final angular velocity, and omega I for initial angular velocity. So now we'll look at the 5 kinematic equations used to solve problems in rotational physics. The first one involves omega F as our subject equal to omega I, the initial angular velocity, plus the angular acceleration alpha times the time t. The second one involves finding the angular displacement theta. It equals the average of the two velocities, so it's omega I plus omega F divided by 2, and that's multiplied by time. Another one for displacement, quite useful, involves omega I again times time plus half times the angular acceleration times t squared. And a very similar one to that one involves the final angular velocity omega F times time minus a half times the angular acceleration times t squared. The final one you need to be able to use involves the final angular velocity squared as a subject equals omega I, the initial angular velocity squared, plus 2 times the angular acceleration times the angular displacement theta. So there are the 5 equations. Very importantly, you'll see here that I've said these are to be used only for problems involving uniform, which means constant, angular acceleration. Keep that in mind. Okay, let's look at some examples involving those equations. Number 1. A centrifuge separates blood components by rotating at 82 revolutions per second. A. What is the angular velocity? So that means we're trying to find omega. B. If the blood travels in a radius of 0.15 meters, what is their linear speed? That means we're trying to find V. And C, if it takes 100 seconds to reach top speed from rest, find the angular acceleration. That's alpha. So, clue for A is that they've actually given you the angular velocity, but they've given it in revolutions per second. So all you need to do is turn that into radians per second to find the angular velocity. And then the clue for B, to find the linear speed, you need to use a simpler equation that you've possibly come across already, involving the linear speed V and omega. Now I haven't given that in this, so I'll give it to you now. Basically omega equals the linear speed V divided by the radius r. So that one there will be used to solve for B. Last clue for C, well, you've been given time, 100 seconds, so let's just say you're trying to find that one. You've got time, and you've got another subtle clue here. You've been told it starts from rest. That means the initial angular velocity was 0. Now, what else do you know? Well, you've got the top speed, which we have to assume was the speed we calculated in part A. So omega F you've also got. So using these 3 concepts, you need to choose one equation that involves the angular acceleration as well, and then you should be able to solve for part C. Have a look at the next slide once you've attempted all 3 questions to find the solutions. Okay, let's look at the solutions then. First one, you have to multiply 2 pi radians per second, because that's 1 revolution per second, by 82. And you should get 515 to 3 figures, assuming this 82 is accurate to 3 figures as well. Radians per second is the unit, of course, for that's a bit messy. Try that again. Okay, that's the solution for A. For part B, we're looking at calculating the linear velocity v, and so we rearrange the equation involving r and omega to r times omega. The radius was 0.15 and we just found omega to be 515. Actually, we'll carry a couple more figures there, 0.22, just so we don't get a rounding error. And we should get 77.3 meters per second for that one. Part C, we need to use this equation, omega f equals omega I plus alpha t. Rearrange and solve for alpha, so it's omega f plus, no, it's minus, doesn't actually matter because omega I drops away at 0, isn't it? So anyway, we divide by t. Simplifying that, we use the 515, we'll put the 0.22 in as well, divide that by 100 seconds, and so alpha equals 0.515 seconds, and that's accurate to 3 significant figures. Okay, let's look at another example, number 2. A large grinding wheel accelerates from rest with angular acceleration of 0.60 radians per second squared. So this tells us that the initial angular velocity, omega I, is 0. We've also been given alpha, and now they're asking us to find the angular displacement theta after 10 seconds, so t equals 10. So we need to use an equation that involves those 3 things at least. That siren's rather annoying, I'll just pause. So the equation we need to use involves those 4 concepts. Initial angular speed or velocity, omega I, alpha, the angular acceleration theta, the angular displacement, and t the time. So go ahead and try and find one and then have a go at solving. The second question, B, is asking you to find the time taken in this case. So you need to find an equation that would help you do that, involving a final angular velocity, omega f, equal to 30 radians per second. Now you have a wealth of information here. You have the angular acceleration 0.60 radians per second squared. You've just calculated, well, in fact, one thing you do have to assume, I believe in this case, is that omega I once again equals 0. So you've got alpha equal to 0.6 radians per second squared. So those 4 things is what you need to use. Once you've had a go at these 2, the next slide, you can pause it and then check the next slide for the worked solution. Right, so for part A, this is the equation that you should have found most useful. The angular displacement theta equals the initial angular velocity omega I times t. Of course that term drops out straight away because we know that's 0, and so it equals simply a half alpha t squared. So substituting in those values, it's a half times 0.60 times 10 squared, and that should give you the answer of 30 radians for the angular displacement. Then for part B, The equation you should have used is this one, the most straightforward one. The final velocity, omega f, equals omega I, the initial velocity, angular velocity that is, plus the angular acceleration alpha times time. Rearranging that and solving for time would give you this simplified equation, because omega I, the initial velocity, was 0. So substituting in the values, we have omega f was 30 divided by 0.60. That gives us 50 seconds.